Alright, so welcome to this next video. In this next video, we'll be doing Newton's method, but now we'll be using some trig functions. So as you can clearly see in our case, f of x equals to cos x minus x. Make sure that your calculator is always in radians whenever we're doing this. So now you have to show that there is a solution that exists for f of x between that. So remember that if you're not sure what your initial value is, you will pick the midpoint between your midpoint in your interval or in your domain, and therefore in our case x of the initial value x0 will just be 1. So we'll continue this process and see, okay, we need to find what the derivative of this is. So what I've done, I've used the formula sheet to just check what the actual derivative that we'll get is. So you can look at cos there. Cos has its derivative as minus sine. So we know that this is going to be minus sine of x. And therefore you then find the derivative of x, which gives you that minus 1 over there. So we then proceed with our method for Newton. So if you want to find out what the initial term is, we'll then go on and substitute 1 and go minus the actual function there, cos of 1 minus 1 over, then we go minus sine of 1 and brackets minus 1. So just a reminder of what is it that we're going to do in our calculator. We'll run an iterative process for this on our calculator to essentially check out what our solutions are, and then we'll be able to take it from there. So let's go straight to our calculator. This is the previous example I had done. So the way we'll set this up again, we'll go 1 is our answer, or driven down that 1 equals to is our answer. Make sure that you confirm that, and then we will set this up. So this is going to be the initial value minus the fraction of the function itself. So this is therefore the cos of 1. No, it's not the cos of 1. It is the cos of our answer. So let's see how we'll be able to do that. So cos of ans, and then we'll go minus the ans there. Okay, over this becomes minus the sine of our answer, and we'll then go minus the answer again, or minus 1. And in this case, the 1 is also just a derivative, so we'll just go minus 1 for that. Okay, so I'm sure you can clearly see this now. When you're doing this, the initial answer that you'll get is that 0.753. So feel free to write it down. So what I'm going to do, I'm going to keep pressing equals to until we get to a number that this converges to. So that'll be the second solution, third solution. We go on, and we can clearly see that I now converge at 0.73985. So even if I keep pressing ans there, that's where the convergence is. So what you can then do, remember that under normal circumstances, you then have to write each and every one of what your approximations were at each step and when you started converging. So please go ahead and do that. I just want, for demonstration purposes, just to show you how that'll get done. And if you go all the way down there, you will see that you start converging to a number now once you get to about x5 again, which is 0.739085. So just a reminder that you can converge after 11 iterations or 12 iterations or even more. It's just that for the examples that I have specifically chosen, they've just happened to converge within the first 5 or 6 steps. So please do continue this process and see how you are able to do that. I hope this has made you understand things a little bit better, and hope that it has made more sense, and therefore I shall see you in the next video.